Okay, can everyone hear me? All right. So yeah, I'll be doing a board lecture mostly. I brought this up so that I can show you some interesting pictures to motivate why we are trying to do this. Right. So I'll be talking about mostly generative modeling via denoising stochastic processes. So there are a lot of words here. First is generative modeling. What does it mean? Denoising stochastic processes. What does this mean? And so on. It will be kind of semi-mathematical. There's a very diverse crowd here, so I hope to convey some ideas to everyone. So this series of lectures will be strictly about the theory behind diffusion models and flow models, and I hope to keep it accessible to as many people as possible. So okay, so let's start with the first question. So how many of you have used Midjourney? Okay, 1, 2, 3, 4. Okay, not bad. Stable diffusion. Okay, a lot more people. Okay, and imagine. Okay, Sundar Pichai will be happy. So okay, so why isn't this moving up? Okay, so the basic question is this. Okay, you're given samples x1 to xn from some distribution p over rd. Okay, can I generate more samples? For example, these images are a distribution over rd. Can anyone tell me how it is a distribution over rd? How would you represent it over rd? Yeah, correct. Yeah, that's exactly right. So this has red, green, and blue values, and for each pixel, there's 256 by 256 pixels, red, green, and blue channels, and then each of them have values from 0 to 1 normalized. Right, so you can represent this as a vector in high dimensions, let's say 30,000 dimensions or something. And then you're given, let's say, some 50,000 samples of this sort. This is from the data set called Celebre HQ. They're all celebrities. Okay, and then let's call these x1 to xn, what we have on the left, and then we feed it to an algorithm, and the algorithm learns some weights, and then we ask it to generate more faces. It generates faces like this, which are not in the data set. These are new faces which didn't exist, right? And diffusion models are considered the best models to be able to do this. Okay, so this is what I call generative modeling. When I say this, we will go into the abstract x1 to xn from distribution P over RD after this. But when I say this, have this in mind. You have these nice pictures. How can I generate more pictures? Okay, so it's not just that. There are more cooler stuff possible here. For example, there's text to image models. I don't know how many of you use text to image models. I give the prompt a cat meditating in the Himalayas. It generates this picture which didn't exist. So this is called conditional sampling. So what I wanted to convince you here is that, okay, this math actually leads to cool stuff down the line. Okay, even though it's boring for a bit, right? Okay. Can we raise this up? Okay. Maybe I'll use the center three things. Can everyone see the central three boards? Okay. Okay. Yeah. Okay. Okay. So we looked at generative modeling. That is given samples x1, xn, distributed as p, let's say their IID. Okay. Generate more samples from p hat, which is approximately p. Okay, so this is the task we are going to tackle, and I'll describe some algorithms for it. Okay, so how many of you work with Markov chain Monte Carlo? Okay, so yeah, so most people here are fairly familiar with it. So before we go ahead, I want to point some differences between Markov chain Monte Carlo and generative modeling. So you have gen modeling, and you have MC. Okay, so you have sample access. That is x1 to xn from P. Okay, and the aim here is each generated sample is meaningful. Okay, so when I say you generate a picture, I don't care about the aggregate statistics of all pictures. I care about each individual picture, right? So MCMC, you have a probability distribution typically of the form e to the minus f of x. Okay, this is a functional description. Okay, you have some kind of a gradient access to this function f, and then the aim here is to find aggregate statistics of P. So this shows up in a lot of posterior estimation problems and so on, where it's intractable to just have this form and be able to understand what kind of statistics it gives rise to. So you sample from it. So both of them involve sampling, but here we care about the quality of each sample. Here we care about the aggregate statistics. Okay. So having made that clear, let's move on to the actual thing here. So okay, let's now think about what it takes to do generative modeling. So to do this, I'll go back to the definition of a random variable. Okay, how many of you have studied measure theoretic probability? Okay, that's great, actually makes my life much easier. So, okay, so we know what a random variable is. Okay, so you have a function f from a space omega. Omega is usually called the measure space, probability space. We can think of it as a source of randomness, and you have a map to Rd. Okay, it's a d-dimensional real valued space. Okay, so we think of if we have an element, random element omega belongs to this measure space, then a random variable is some function f of omega, right? So this y, we observe this y, we don't observe this ground truth omega, and we call this a random variable. Where is the source of randomness? It's this, roughly, when you think about these things. Okay, so this is the random vector in this case. Okay, so now let's ask the question, what do we need to generate randomness? Okay. Okay, so the first thing is we need a source of randomness, that is omega. Okay, in practice, you think of it as, okay, there's a random number generator, or maybe you can toss a lot of coins and generate some binary bits, or there's something called pseudo-random number generators and so on. They generate some simple distributions such as Gaussians or Bernoullis or uniform distribution from 0 to 1 and so on. You can treat this sequence of random variables generates as the source of randomness, that is the measure space omega. Okay, and B, or number two, a function f, like I showed here, to shape it. Okay, we don't actually care about Gaussian random variables because it's easy to generate. We know its shape, we know everything about it. So we actually care about, let's say, a space of images, a distribution over images, right? So we need a function f to appropriately shape this tractable source of randomness, that is a set of a Gaussian random variable, and we suddenly want it to look like an image. So we want to apply f to omega, and we need it to look like the distribution we have. Okay, so this is the hard part. This a lot of people have figured out how to do it on a computer, how to do it efficiently, and so on, how to make it robust to various hardware details and so on. We will take this for granted and we will study this. Okay, so now how do we obtain the function f, right? It's obviously it has to be some kind of through some kind of a neural network, a learning procedure, because we are given data. We collect some kind of aggregate statistics about it and then learn the function f. Okay, and since we are in 2025 now, we need to do it with the neural network. Okay, so there are many early ideas here. Okay, let's think about some early ideas. So, does anyone know what are the early ideas to do generative modeling algorithms before diffusion model? Exactly. So the first one is called a GAN. This is called a generative adversarial network. Okay. So I won't go into the details of it. It poses the question of generation as a two-player game. So there's a generator network which generates some distribution, and there's a discriminator network which tries to attempt to classify it, says whether it is from the ground truth or not. Okay, this was initially very successful, and it was state of the art until about 5 years ago. And the second one is VAE. Does anyone know what a VAE is? Okay, good. Variational autoencoders. Okay, so variational autoencoders too are more stable to train. It's very easy to train, but they suffer in terms of quality. GANs have high quality, but it's very hard to train unless you find the magical hyperparameters. And VAEs are very easy to train, but they suffer in terms of quality. It's very hard to get good quality. Okay, so but now, so so both of these take this viewpoint. So they'll say, okay, I'll give you Z, which is a normal random variable, standard normal random vector, and I'll learn f such that f of z has the distribution approximately equal to p, which is my target distribution. Okay. So this is what GANs and this do. And one hypothesis is that doing this is hard. You can't just learn this very intricate function which just calculates something on a Gaussian random vector and then suddenly gives you something very intricate and meaningful, right? So okay, so therefore these days we have the SOTA models are diffusion or flow based models. Okay, so this has many advantages. It is easy to train. I'll tell you why it would be easy to train in the one of the later lectures, or my hypothesis as to why it's easy to train. But it is slower to sample. And it gets the best quality. Yeah, but this is not such a bad trade-off, because you're getting something easy to train, which is repeatable. You can train it many times, and you have very good quality. It's just that you need more compute to sample, but it's okay. We have all these big data centers which will sell us compute, so we can kind of sample it. Okay. Okay. So topic of the rest of my lectures is unraveling what these do and what these diffusion models mean. Okay. Is this board too far away for some folks on that other end? Okay, good. Okay. Okay, so like I said, VAEs and GANs think of learning this function f directly as a neural network theta. You tune this theta such that this is approximately p. It's hard to actually learn this function. Okay, so can we think of this differently? That is, the diffusion models think of this differently in the sense that can we generate slowly? All right. So basically, what we want to do is slowly transform noise to signal. Okay. So, okay. So now let me ask you a question. How do you change something slowly? What is a proposal? I have some random vector Z. I want to slowly change it to look like an image X. Okay. Can you tell me what kind of system would do that? Just an example of something which slowly changes to something else. Huh? Sorry? Okay. Okay, so the one example would be ordinary differential equations. Okay, so because you don't just get one function, call, and then you just suddenly get whatever which is drastically different. It has to be continuous, and it's a solution and so on. Solution of a differential equation which is continuous. Okay, so first example we'll deal with is an ordinary differential equation. Okay, this is of the form, let's say dxt by dt is equal to vt of xt, right? And here we want x naught to be a standard normal Gaussian random variable, and we want x1 to be the data distribution. Okay, so okay, so let's interpret this a bit. Yeah. Because okay, it's a hypothesis. Okay, I'm just putting it that way to be able to connect the dots. But initially they tried to learn it this way, and it did not work very well. Okay, what if the thing is that you learn the process to generate it, right? So, and that actually works in practice. So, okay, so we want this to happen. So to use the parlance, so this we can call it a velocity field. Okay, what does this velocity field do? It will tell at time t, you know that xt is at some value. It will tell it how to move. That is, it will mention its velocity, and you will be able to integrate this. So that is a typical solution to this. If you start here, it would look like this in one dimension. So if you look at x of t, and or rather xt, and this is t, if there's some velocity field, it would kind of tell you this. Yeah. Yeah. Mm-hmm. Mm-hmm. Correct. Okay, so no, that would not be true, because okay, so there are many nuances here. One is that okay, let's say for the sake of the talk, we are dealing with something which has a density, a finite KL to the Gaussian and so on. Second thing is, yes, images are hypothesized to be a smaller dimensional manifolds, but if you add a little bit of Gaussian noise to it, it still looks like a perceptibly like an image. So you can approximate it with a thing with a density over RD. So, and another third thing is that people believe that neural networks actually are able to leverage low dimensional structure. Right? Even though your data is in high dimensions, it will understand the data in low dimensions by extracting the right nonlinear features. So especially convolutional nets and transformers and so on. So I think those combination of things are being used to explain why it actually works. But yeah, of course, there's a lot. It's an area of active research. So, correct. So yeah. So basically, if you have a 256 by 256 by 3 image, it doesn't mean that it can't be compressed further, right? You can make a much smaller state space out of it, and that's what let's say autoencoders, variational autoencoders, were not very good at generative models, but they're good at compression. So you compress with that, you go to a smaller latent space, diffusion, and then decode. So yeah, so that still keeps these alive. That's how, for example, stable diffusion works, or most diffusion models work, or large scale. So Yeah, but still the question remains that, okay, what if that is also low dimensional compared to their 64 by 64 by 3? Again, that I don't know. Maybe there's a low dimensional structure there too. Yeah. Sorry? Yeah. Yeah. I would say that, okay, so people have looked at, let's say, I'll come to this in the last few lectures, in the sense that if you, it hinges on a learning problem called score matching, right? Score matching in the min-max rates are, worst case, it is exponential in D. So if you're in large dimensions, there are too many disconnected open balls of constant radius, right? Exponentially many. So that's why it's very hard to do score matching there. But what happens is that images are actually low dimensional. So that's why you're able to get away with this. Mhm. Mhm. Yeah, so a lot of recent papers in learning theory want to argue that, okay, if there is a low dimensional structure, then it's easier to generate. Correct, in the 10,000, but it actually learns what matters to it to generate the distribution. But I don't know, I don't think it's a rigorous proof or anything, but people have explored some toy examples in that direction. Okay, so I gave you one example ODE. Can anyone say what is the second example I'm going to talk about? Exactly. So the second one is a stochastic differential equation. Okay, so how many of you have done a stochastic calculus course? Okay, a fairly decent number of people. So we have here we had a velocity field, there we call it a drift, and the second term we'll call it a diffusion. You have something like v of t comma xt dt plus, let's say, root 2 dbt. Okay, this is a Brownian motion. Okay, so why didn't I write this as dx by dt is equal to something like a physicist? Exactly. Brownian motion is not differentiable. So it exists. It's a very rough path, as you can call it, and this has to be properly understood what it means to integrate this out. So this is not a differential equation. Technically, it's an integral equation, and the integral equation can be defined once we define what an Ito integral is, right? So we can solve differential equations technically as integral equations even when things are not differentiable. So okay, so why is this bad? Because the solution to it, why is this harder to understand is because a typical solution to this kind of an SDE looks like this. I hope you can see the zigzaggy motions here. In the talk in the morning, I'm sure an algorithm can detect that this is hand-drawn Brownian motion. Doesn't look like a machine-generated one, but but yeah, so it looks like this. So what I'm saying is it's not differentiable anywhere. It's actually Holder continuous with an exponent less than half. Okay, so it's not even Lipschitz anywhere. So it has to be properly interpreted, and so we will study these two paradigms of generative modeling because they're very related. The techniques are very similar, and you can go back and forth between these two kind of ideas. Okay, so this is called a flow model. Okay, and this is called a diffusion model. Okay, all right. So okay. Correct. And a final condition. Yeah. How do we find correct? Yes. Yeah. That's the flow. Yes. And the second one is again x0 is something, and then xt is something, and how do you find? Okay. So now I want to actually learn this. So what should I do? What should I learn? What can I tell you so that you can I can give you a Gaussian and something, and finally obtain an image? What should I learn? Exactly. We need to learn the function Vt of xt. Right? We need to learn the drift Vt of x. Okay, so it's a function of time and space. So we need to learn it from data x1, xn, which is distributed as some distribution p. Okay, so the second question is, I don't know if I'll have time to get to this in the course of the lectures. So, okay, suppose we are given this V, how do we simulate this continuous time stochastic processes? Okay, this is the question of inference or discretization. Actually, you might think that, okay, I'll put in a straightforward Euler or Euler-Maruyama discretization, it will work well. But no, that's not true. You need to do something, you can do sometimes things much nicer. But yeah, maybe if we have time, I'll be able to cover that topic as well. Okay, so what we will do on a high level is we will develop theory to answer these questions. Okay, yeah. In which way? Images are not the ODE. We just think that images are a distribution, which is true, right? It's a distribution in RD. Yeah. That ODE learns this. That's a hard question. I mean, because okay, so like I'll show later, it's that okay. If you can, we have an algorithm to learn VT and the drift or the velocity field. Okay, so the right question to ask is why is it that when I have the data distribution to be this, why can I efficiently learn that? So the answer lies to that in inductive bias, or maybe it's just that it's a low dimensional distribution which actually masquerades as a high dimensional distribution. So on. Right. So once we go to the learning part, then we'll have to. There are more open questions to understand why is it so. It becomes clearer. So we'll actually deal with the general theory now. So yeah, yeah. Okay. So first we'll do some mathematical theory, derive Fokker-Planck equation, the continuity equation, and so on, which will actually allow us how to go about thinking about this velocity field, what it does to shape the distributions. Okay. So the second thing we'll do is we will derive learning algorithms to answer these questions. Okay. And then if time permits, I'll try to do, how to do discretization of these and do inference. And then of course, there are more advanced topics like two rectification, discrete diffusion models, and so on. Discrete diffusion models are basically discrete Markov chains, which will generate discrete data in a finite space. But people call it discrete diffusion models in this field. So, okay. So, but these two things will definitely take care of in the next few lectures. Okay. So to develop the theory, let's ask more fundamental questions about the ODEs and SDEs. First, we'll deal with the easier case of the ODE. Okay, I'm given a velocity field. Okay, this basically tells at time t, I'm at position x, what should be my velocity. That's what it tells me. Okay, so we have the ODE, which is the initial value problem, as this is called in the field. So we'll call it Vt of x t. Okay, x0 is some initial point x0. Okay, this is called an initial value. Okay, the two questions we'll ask is, when can we solve it? Okay, when is the solution unique? Okay, so does anyone know off the top of their head what is the basic theorem in this field called? Yeah. 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 Correct. Wait, what is this theorem called? The name of the theorem. Okay. Okay. So what you're talking about is called the Picard-Lindlof theorem, right? It's a very famous theorem. I would really recommend you check out its proof. It's a beautiful application of Banach fixed point theorem. If you know functional analysis or something, it's a very nice application of why thinking abstractly about operators is useful, because you can prove beautiful theorems like this. And there's something even more general than Picard-Lindlof. It's called Carathéodory existence theorem, which is more measure theoretic in the sense that you don't even need some kind of continuity in time, but you'll be able to do it. But for the sake of completeness, let me actually state the Picard-Lindlof theory. Okay, like I said, there is a domain D, which is a rectangle in R, let's say RD. Okay, and this is a closed box. Okay, and let B of t comma x be a continuous in T, and 2, it is Lipschitz in X. Okay, how many of you know what Lipschitzness means? Okay, so that makes my life much easier. Okay, so then this implies there exists an epsilon greater than 0 such that the ODE has a solution for t belongs to t naught minus epsilon comma t naught plus epsilon. Yeah. Okay, so you can assure that for a small amount of time, it does not, it has a solution. Okay, so can you tell me why we are not able to ensure that the ODE is not solvable for all times t, for all future times till infinity, using these assumptions? What do you mean? Yeah, closed box means it's a rectangle. Yeah. Yeah. It is bounded. Yeah. A box is a bounded. Let's say, yeah, right. So it's Lipschitz. It's locally Lipschitz in any box. I give you any box, I'll tell you it's Lipschitz in that box. Yeah, no, sure, it's continuous. Let's say it's not even dependent on time. Why can't you solve it till time infinity? Yeah. Why doesn't it go to infinity? It might actually converge to a finite number. Yeah, the maximum allowed epsilons can be form a convergent sequence series. Okay, so the reason you can't do that is because there's a very simple counter example which you learn in the ODE course. it shows that, okay, if it is not globally Lipschitz, it's only locally Lipschitz, right? Then it can blow up in finite time. Okay, so you can actually solve this as a nice exercise. I won't solve this ODE. So you consider dxt by dt is equal to xt squared, where x naught is equal to 1. Okay. And you will see that at time 1, it will reach infinity. You cannot solve this for arbitrary amounts of time. It will just go to infinity. Right. So this is a function which is an example of something which is locally Lipschitz in every closed box, but you cannot have global solutions to this. Okay. Yeah, that's called a global Lipschitz function. That's called a globally Lipschitz. Yeah, right. So if you have a globally Lipschitz function, you can ensure that you can solve it for this, and actually that we can get a quantitative bound for this epsilon, and that's what enables us to be able to do that. Right. So there are many more general kind of results exist, like Carathéodory existence theorem, which is more measure theoretic. There you actually don't need continuity in time. You just need it to be measurable and bounded in time, locally bounded and measurable in time. Of course, that's beyond the scope of this kind of a lecture series, so I'll leave it at that. Okay. Okay. So and then okay, of course, we can also talk about the uniqueness of this solution. This solution is also unique. Or rather, the maximal solution is unique. That is, right before it diverges to infinity, whatever the solution you have, we can solve till the maximum amount of time. That solution is unique because of the Lipschitzness. So, okay, so now we saw that, okay, we pose this problem. I'll tell you a velocity field under fairly general conditions. You're able to solve this. You're able to integrate this equation, initial condition, and you're able to obtain a whole trajectory xt. Okay. So, but we don't care about a trajectory. We care about the distribution at time t. Okay, so we ask a much harder question. A harder question. Okay. Suppose x naught, so that is the initial value x naught is a random vector. Okay. Let's call its probability density, that is as p naught. Okay. It's we'll say that, okay, it is distributed as p naught, and we'll also abuse notation and say that the p naught is the density of x naught. Okay. So okay, then we will solve dxt by dt is equal to v of t comma xt. Okay, and then we'll say that xt is distributed as some distribution pt. Okay, so to give you some kind of a picture, okay, so we have x naught, which is like a fairly nice kind of thingy, these are all the possible initial conditions. Okay, and this each point evolves as the ODE somehow, and then we start getting these strange looking points which correspond to the solution with each initial point with this distribution. This is p naught and this is pt. Okay, so what is the shape? So roughly speaking, in common words, it is what is the shape of pt. Okay, so I'm guessing since a lot of you know have done measure theoretic probability, you also know about probability densities and so on. So I'll skip the definitions of that. Okay. Okay. So yeah, so I've set this up. We can actually see PT as a push forward measure of the solution of this ODE of x naught, right? So if you know what a push forward is. Okay. Okay. So long story short, the PT is a solution to a partial differential equation called the continuity equation. Okay. How many of you have dealt with continuity equation? Okay, a fair number of you have. If you have actually done physics or or fluid mechanics or something, it actually tells you that it's a mass conservation, right? So it basically says, okay, if many particles are there or a field and things are moving in that field, in this velocity field, the mass doesn't vanish or add up anywhere in any place of right? It can only move through space. Okay, so I'll, to write this out, what this is. So you have partial derivative pt of x plus divergence x of v of t comma x pt of x is equal to 0, where v of t comma x is this velocity field. Okay, do you know what a divergence is? If anyone doesn't, I'm happy to just define it quickly. Yeah, okay. A divergence in x is, okay, suppose we have a function f from, let's say, rd to rd. Okay, so what can we write? So if you write as f of x1 comma xd is equal to f1 of x, f2 of x till fd of x. Okay, now what is the divergence? So divergence of f of x is equal to summation I dou by dou xi f of fi of x. Right, so this kind of gives you the flux. If you have a rectangle, it will tell you how much the flux differential across this is, so that you know what direction things flow in. Basically, roughly the intuition. Yeah. Which one? D. This one. This one. Picard-Lindau. This. Oh, D is a rectangle. It's a closed box in D. So it is continuous in time in D. In D. Initial condition. So right. Sorry. Let's say it's minus epsilon to plus epsilon. At x0, it's an initial value problem, so you can actually extrapolate it back in time and also forward in time. So V takes, no, yeah, so V takes R plus comma RD, R plus times RD to RD. It's a velocity. Sorry? It's a closed bracket. I mean, if it's an open bracket, you can always make it a closed bracket because you take epsilon over 2. That's all. Square. Yeah. I mean, it's a small technical detail. You can just make epsilon over 2 and go from closed or open to closed or open. It's an existence theorem. That's why it doesn't matter. This one, it's a divergence. The dot means a divergence. Okay, if it is confusing, I'll use div of x, div of f as this. Henceforth, that should be less confusing. Okay, so now, yeah. This PT, yeah. Correct. Right. So because at P0 we are given a Gaussian, and at PT we are given a different density. So we don't care about a single. So when is my chosen velocity field correct? When P1 is my image distribution, right? I'm not enforcing yet. I just want to see if I'm given some velocity field, what is the trajectory? Then we'll figure out what is the right velocity field. Sample from this, like a density. Like for example, if I use it in a very rough sense, if a distribution is typically in the set, it's the shape of the distribution, let's say. I'm by shape, I'm in density. Yeah. So yeah. So okay. So actually, I want to say that this holds even when the density does not exist. You might be wondering how are you partially differentiating the thing which is Dirac delta and so on. Physicists do it all the time, but I'm not a physicist. But there is a notion called existence in terms of solution in terms of distribution. okay, which I don't know how many of you have done functional analysis or PDE theory, weak solutions, okay? I guess a few of you have done it. So we can actually differentiate very, very large classes of functions, even if they tell you it is not differentiable, but the derivative exists in the sense of distribution, okay? And we will use that theory to show the existence of this, okay? So it's called a generalized function. It exists as a generalized function. Okay. So first, some intuition about this. What does it show? This shows how much the density of X is changing at each point of time through time. And I guess what we would guess is this will show how much is moving into point X and how much is minus how much is moving out of point X. Right. So a change of rate of change of density at each point. Over time, that means it's probably going up. Yeah. If it's increasing, it's going in. Correct. Yeah. Conservation of mass. That's exactly it is. But it might just look like conservation of mass, but it has a very deep structure, and it's especially important to something called Wasserstein gradient flow. And this can be seen as a gradient flow in the space of distributions. A lot of things have this form, and yeah, in a huge amount of generality. So I don't know if I'll have time to go into how important this continuity equation is to understand dynamics in the space of distributions. But take my word for it that it is very fundamental. Yeah. Correct. Yeah. Probability distribution. No, but you can write it for general measures. It will still be mass conservation, but it just won't integrate to 1. No. What I'm saying is we start with this ODE. This is what we want to implement. So if I say what is the distribution of xt at time t, this is what it calls us. Yeah. But yeah, that will come there because something else gives rise to that. Other kind of things. Yeah. Okay. Okay. So we will derive this via something called witness functions or test functions. Yeah. PT is the densities. Okay. So yeah, we will be going back and forth with the continuity equation. So if you want to write it down, I think this would be a good time to write it down because this is very important to what we will develop, the entire theory we will develop over the next few lectures. Okay. A Fokker-Planck equation has an additional term here, a diffusion term. But Fokker-Planck equation can also be seen as a continuity equation, which I will come to in the derivation of reversal. So, okay. So now we will derive this via test function theory. So who knows what CC infinity class of functions is? Okay, 1 person, 2 people, 3, 4, 5. Okay. Yeah. Right. So specifically write down what I'm talking about. Okay. So this is a set of all continuous functions. Okay. Such that it is infinitely differentiable. That is, all the derivatives of all order, all partial derivatives of all order exist over this set. And this C means that it is compactly supported. Okay. So that is continuous functions, infinitely differentiable, compactly supported. Yes. In the topology of 0 to T cross RD, someone asked me if it was an open or closed set. Here it actually matters. This has to be an open set for the math to make sense. So it cannot be a closed interval here. Right. Okay. So what does this mean? Roughly, let me give you a feel for this. If you're not very well versed in topology, it's fine. So what does this mean? If phi belongs to this CC infinity of 0 comma t cross RD, then first thing we have is phi of 0 comma x must be 0, right? Because this is the boundary of an open set and it cannot be compactly supported if it has a non-zero value there. Okay. And the second thing is similarly phi of t comma x is 0. So it vanishes at both endpoints. And the third is phi of small t comma x is equal to 0 for all x greater than some rt. Right. So if you go off to infinity after a point, it's 0. It doesn't have any information. But what this RT is, it depends on function to function. It's arbitrary, and you can construct an arbitrarily large compact support for these functions. Okay. We can also think of these. So these are called test functions. Okay. So test functions are especially useful in understanding PDE theory. And like I said, you might have studied physics in undergraduate, and they would say come up with this function called Dirac delta, which is 0 everywhere except at 0, where it is infinity and it integrates to 1. It's literally not a function, but this test function theory allows us to interpret it as a functional, right? And similarly, physicists used to go around differentiating Dirac delta and got minus delta whatever prime of something. Right, so that again should be interpreted. How do you differentiate something which is infinity? You differentiate it by treating this as a treating this as a generalized function, like I'm about to say. For example, this continuity equation, like I said, it need not require a density pt of x. It can even hold for singular measures like Dirac deltas. So to do that, we need this space of test functions. Okay, so physicists call integrating against test functions as smearing. Against this, and many field theories only exist when they're smeared, right? They don't exist as functions. Okay, so a lot of people, this is very foundational in the theory of functional analysis, and even Fourier analysis is developed using this test function theory, and I'll show some elements of this. Okay, so okay, the first question I ask you: if we know the value of integral p of t comma x mu of x dx. Okay, this need not have a density, even though I wrote it like a density, it's just integration. For all p belongs to our test function class, CC infinity, right, is mu unique. Which part is? If we know the value of, okay, sorry, it's very illegible. Integral p of t comma x mu of x dx. Can you read it now? Okay, for all phi. Okay, whatever phi you tell me. Okay, I'll tell you the value of this integral. Okay, can you uniquely determine mu? No, it's just mu for now. Okay, we can actually take mu t of x. Yeah, correct. Yeah, I don't need it, but okay, I'm just giving a motivation. Let's say if I tell you for everything, can I uniquely determine this mu? Let's say t is not 0 or t. Can I uniquely determine it? Yes. Why is it? Yeah, correct. If you know the more like if you know the but that is in 1D. You can do it in for every half space, right? So every rectangle you get it and then you do it. Okay, so then there are basic things called mollifiers and so on, which will allow you to get better approximation of these indicator functions through CC infinity functions, and you will be able to find the probability of every closed box, and if you know the probability of every set, then you know the probability distribution. Okay, I'll do it. Wait. Okay, so suppose let's think of to arbitrary precision, yes. Yeah, that's the whole point of this. Yeah. So, right. So the point here is, this is a half interval argument. So let's think of RD. So if I tell you the measure of mu of a comma b for all a comma b in R, I know the probability distribution, right? Such that b greater than a, right? Or b greater than or equal to a, right? So how do you do this? So now how do you get a CC infinity function out of this? So let's think of this. Okay, this actually is mu of a comma b is integral of this function. That is, let's call this function chi a comma b. So therefore, mu of a comma b is equal to integral this step function a comma b of x d mu of x. Okay. So now you know. Okay, for if I tell you this integral for all a comma b, this class of functions, indicator functions, then you know the distribution, right? So now we go one step further, but this is not differentiable. This is not a very. It's not even continuous. It's not a nice object to deal with. So what you'll do is you'll actually go and let's say this is a b. You'll have successive approximations of CC infinity functions, which start looking like this, right? Okay, so this was your a, and this is your b, and this is 1, and this is 0. And now slowly you'll go on making this this closer and closer to this function. Okay, there's a theory of mollifiers which tells you that such functions exist. Okay, you can actually look up Friedrichs mollifiers, okay, which exactly do this. Okay, this is very interesting stuff from the 50s and 60s, which account this. So therefore, we know that if we are given this, we can arbitrary precision, we can estimate mu of approximate mu of a comma b. If you know all of those, then you know the probability distribution. Yeah. Yeah, but right. But I just want this. Which one? Truncated Fourier transform would be compactly supported. Yes. Yeah, that's what a Friedrichs mollifier is, a bump function, example of a bump function. Yeah. Yeah. So yeah, so like I said, this is the statement I made. So if I know this integral over mu for every phi, then I know mu. So we will use this. So we will, whenever say equality of some equation, then I know that integration against all the functions in this should be equal to some quantity I told you about. Most likely it is about 0, right? So then I know that this quantity is 0. Yeah, correct. So slowly it will become less and less. I mean, its derivatives start blowing up, but it's still CC infinity. So it's in the class. Okay. Now I think we have all the tools to derive the continuity equation. Actually, this is not the continuity equation. This is the continuity equation in the distribution form. So let me derive this exactly. Okay. So now we have the original equation, that is dxt by dt is equal to b of t comma xt. Okay. So now we have the first observation. For any CC infinity of the function which I told you, we have p of xt 0 t comma xt minus phi of 0 comma x0 is equal to integral 0 to capital T d by dt of phi of t comma xt dt. Of course, this we know from fundamental theorem of calculus. This is almost certainly true. And now observation 2, phi of t comma xt minus phi of 0 comma x0 is equal to 0. Why is this? It's compactly supported. That's why it is 0. Okay. So now we can combine these two observations. Okay. So now we'll go to observation 3. So this is the chain rule. Okay. So d by dt of t of t comma xt is equal to partial derivative of t comma xt plus gradient phi of t comma xt comma b of t comma xt. Can you tell me why this is true? This equation. Total derivative rule. This is one of the fundamental theorems of multivariate calculus. Okay, so this is all it takes to derive the continuity equation. So now we'll take observation 1, 2, 3 and combine them together. So what does it show? It shows that for all phi in the function class I told you about, 0 must be equal to integral dou by dou t p of t comma xt plus v of t comma xt comma grad phi of t comma xt dt. Okay, if something is 0 all the time, then if you take expectation of this, it should be 0 all the time. So now let's say x naught is distributed as some p naught, and we know that xt is distributed as some pt, and we'll take expectation on both sides, okay, which to our surprise turns out to be 0. All right. So therefore, if you take expectation on both sides, so you have expectation of integral dt of dou by dou t p of t comma xt plus grad phi of t comma xt comma v of t comma xt is equal to 0. Okay. So now, do you know how to change what theorem you need to invoke to interchange integral and expectation? Yes, Fubini's theorem. We apply Fubini's theorem. Of course, to apply Fubini's theorem, we need to show that Vt has is a finite expectation over Pt, which we'll throw in as an assumption. We'll assume that Vt is as smooth as necessary to have solutions and then to be integrable and so on. We can think of it as bounded even if we wish, and so that we can do all these operations without much problems. Okay, so Fubini's theorem implies integral over dt, right? Integral over pt of x of dou by dou t phi of t comma xt plus gradient phi of t comma x v of t comma x is equal to 0. Okay, and this holds for all p belongs to cc infinity of 0 comma t times rd. Okay, so mathematicians call this the continuity equation. So this does not look like what I wrote you before. Right? Did I do a bait and switch for you? So what I told you was the continuity equation was this nice partial differential equation. Let's say divergence of Vt of x, Pt of x is equal to 0. I told you this was continuity equation. Now I'm telling you that this strange looking line is the continuity equation, right? So how do you connect these two? It's integration by parts. So actually, this is an old joke among mathematicians, that there was a very, very famous mathematician who got the Presidential Medal of Science or something in the United States, And then he went and someone asked him, what did you do for this? He said, I integrated by parts. So, I mean, it's not even a joke because most of the things like this can be formalized using integration by parts. So usually things which of this form, this can only exist when you have smooth densities. But then how do you extend it to more important things like singular things, Dirac deltas, derivative of Dirac deltas? It would have something of like this sort. You do the computations for something smooth, and then you just extend the definition everywhere to more singular things. So more importantly, this definition does not assume a density. You just need to be able to integrate against this quantity, like a measure would do, right? Right. So, okay, let's actually derive this using integration by parts. Okay, or yeah, there's a dx here. Or we can call this a dpt of x, which is more appropriate notation. Okay, so I have actually 3 minutes remaining. So I'll leave this as an exercise for the next time. Okay, use, huh? 13 minutes left. Okay, so 10 minutes left. Okay, 8 minutes left. Okay, got it. Okay, so I can integrate by parts. Okay, so okay, let me show you the magic of integration by parts. Let's assume that PT is sufficiently differentiable, it vanishes fast enough at infinity, and so on and so forth. So now we have this integral dpt of x, sorry, integral pt of x, pt of x times dou by dou t, p of t comma x dt, integral from 0 to t. Okay, we know that this must be equal to p capital T of x, p of t comma x minus p0 of x, p of 0 comma x minus integral dou by dou t, pt of x times p of t comma x dt. Okay, so now what is the value of this? It's 0 because it's by definition 0, right? So now we can actually go and interchange the differentiation. You can actually plug in the differentiation from phi to p in this, and then we'll get a minus sign. Okay, and then I'll leave this as an exercise to you guys, which you can hopefully, if you're willing, you can complete it for tomorrow, which is integral pt of x 0 to this is over rd dx times grad phi of t comma x v of t comma x dx. This must be equal to integral phi of t comma x times divergence minus of this times the divergence of v of t comma x times pt of x. I'll leave this as an exercise. This is not very hard. This is the same old proof, but applied in space instead of time. And the boundaries at infinity instead of 0 and t. Okay. So, all right. So now we'll combine both these elements with this equation. Okay. So now what is the continuity equation? We see that integral p of t comma x times dou by dou t pt of x plus divergence of vt of x pt of x must be equal to 0. This is for all p in the class I told you about, in the test functions class. Okay, so do you remember the theorem I just erased in that board? When I said, if I tell you the integral over all test functions of a certain quantity, do I know that quantity uniquely? Yes. So that's equality to 0 in the sense of distributions, in the sense of test functions, right? So by definition, this implies the continuity equation in the form that I told you, which is Okay, so yeah, so this is the fairly semi-rigorous derivation of the continuity equation. I mean, I've left out many asterisks here, given that okay, this is smooth enough, this is decays fast enough, and so on. But modulo that, this should be a rigorous enough treatment of this. Okay, so yeah, I'll let you ask any questions you might have. Yeah, its integral should exist with respect to PT. V at infinity. Yeah. Yeah, you have any questions? No? Yes, maybe. Correct. Yeah. See, okay, if you know, have an indicator function, right? Which is one in the interval you want and zero outside. If you know the integral over that function, you know the probability distribution. Modifiers and then approximating this characteristic function, right? Right. Okay, so this is a very fundamental equation we'll be dealing with this time, which we have derived today. Tomorrow we will power through stochastic differential equations and derive something called the Fokker-Planck equation, right? Which is the equivalent of the continuity equation in that case, and then we'll bring them all together and see how we can learn this VT so that we will get a diffusion model. Oh, like that. I think the physicist derivation is you draw a box. Okay. No, I mean, I'm not. Okay, so, right. So, what is the velocity here is there's a, okay. So, what is the amount of thing going in? So, this is V here, let's call it V1. Okay. Velocity here. And what is the velocity here? Let's call it V2 or V0. Okay. What is the total amount of influx into this? It is V1 minus V0. Divided by whatever, divided by length. Let's call the length L. Okay, sorry. Let's say no. V1 minus V0. Okay, and then we have sorry. Yeah. So into time, which is delta, small amount of time delta, and this is a change in mass. And then okay, what is the mass here? The mass. Okay, actually, there's a density here that is V0 times P0. That is the entry coming in. And then there is a V1 times P1, which is coming out, right? And then I think that we need to multiply it by the length of this thing so that we know what is the total flux coming in. And then I think after a time delta, this will tell you change in mass. And somehow magically this comes in the denominator and this becomes the divergence, right? It's a spatial derivative, as you can see, right? So, and yeah, correct. Exactly, that's what this says. But yeah, this is yeah. Sorry, which one? And the T, yeah. Oh, this is not an expectation, it's an inner product. It's a Euclidean inner product, yeah. Yeah. Which one? This one? This E is over xt. Xt is a random variable. And that's why you get a PT here. Yeah. 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 Let's say it's a Gaussian for all of purposes. Yeah. Yeah. There are some function conditions which will ensure that. Yeah. Yeah. So what happens to the entropy of this random variable? What happens to some property of this random variable that will upon time? I don't know, because you can always have flows which will kind of converge to zero, right? I mean, I don't know if entropy will. I mean, you can always have data processing inequality, which shows that, right? For example, all convex functionals can be kind of this thing, but yeah. Otherwise, yeah, it depends on the thing you're asking. I mean, oh yeah, for sure. It can show you, for example, if it's a negative measure, it will always stay a negative measure, and that's how you show uniqueness to the solutions to this. Cool. Yeah. Yeah, I'm happy to talk offline if you have any more questions.